Good morning, everyone. I am Edoardo Bori from Università Libre de Bruxelles, and today I'm going to expose you our study on biomechanical analysis for different level of constraint in TKA during daily activities. When we are dealing with total knee arthroplasty, we have to keep in consideration that we have a different level of constraint according to the model that we are implanting, and those level of constraint can start from, as an example, a cruciate retaining prosthesis in which the posterior cruciate ligament is still present in the patient. So we want to leave the possibility for this ligament to act. So we are not constraining that particular series of degree of motion. But in case this cruciate ligament is not acting as it should, we can proceed with a posterior stabilized, in which the action of the ligament is covered instead by an artificial system of post-cam, as represented in figure. And in case also the collateral ligaments are not working properly, we can proceed with a CCK, a condylar constraint knee, in which, in this case, also internal-external rotation is constrained by the design of the prosthesis itself. If the situation of the patient is then really heavy, let's say, we can proceed with a hinge TKA, which has an even higher level of constraint compared to the others. If this concerns the relation between the femoral and the tibial components, we also have to consider that we can have differences in terms of the interaction between the tibial component and the tibial insert, as we can have mobile bearing prosthesis and fixed bearing ones, in which the insert can or cannot rotate compared to the tibial component. Then, talking about the insert, we can also have various design of insert, and this also alters the constraint of the prosthesis. On the left, as an example, we have a more flat one, while on the right, we have a congruent one. And as you can imagine, this also change how the prosthesis is acting. So, as we have seen, we have a different set of implant among which we can choose. And the surgeon has to decide which is the best one for the patient, both in terms of short and long-term survival. So how does he decide how to proceed? He has to keep in consideration which are the bone and the soft tissue status of the patient, and therefore what he can afford to insert in the patient. But what are the outcomes? What are the effects that each of these different design parameters have on the bone stress, on the stress distribution on the implant, on the contact areas? This, biomechanically speaking, it's still not covered by clear and univocous guidelines. Therefore, the scope of our study is to perform a comparison among different degree of constraint of these TKAs and compare these different outcomes during three typical daily life situations in which the patient can find himself. In order to perform this kind of comparison, the way that we decided is to proceed with finite elements analysis, that is in silico simulation that afford us to have these clear comparative results. In order to achieve this objective, we started with the first ingredient, let's say, that is the geometries. So we took a sawbone, as it's usually done in literature for this kind of studies. We have CT scans of this sawbone, and we perform a reconstruction for the 3D model of the bone. We divided it in cortical and cancellous for reliability of the model, and then we proceed to address the soft tissues. We kept in consideration collateral ligaments and the cruciate one when present. And for the medial collateral ligament, we consider two different bundles, and all the insertion points were taken from the literature. Then we have to define the design of the prosthesis that we want to consider. But as you can imagine, we have a wide plethora of prostheses available on the market, and we just want to check which are the difference due to the level of constraint, not to brand-related design changes. Therefore, in order to perform this comparison, maintaining the most possible accuracy of results, we decided to proceed with all the products in the same family. So the only parameter changing was the level of constraint and not other kind of design parameters. So we considered for mobile bearing 2 different implants, one with cruciate retaining and the other one with ultra congruent cruciate retaining. And for the fixed bearing, we have a posterior stabilized and a constrained condylar knee. So we define the prosthesis. Now we have to perform the virtual surgery, let's say. So we took the prosthesis, we selected a press fit approach and a mechanical alignment. Then we proceeded by performing the cuts in the bone model that we obtained, and we positioned the implant accordingly. Since we proceeded with a press fit approach, we also implemented the series of contact to represent this surgical approach. We then applied a series of mechanical properties, again, from the literature, from also previous studies in this validated protocol that we used. And for the bone, we consider transversal isotropic for the cortical in order to be more realistic in terms of reproducing what the bone fibers are aligned for the femur and the tibia. As you can see, we also implemented a pre-strain for the collateral ligaments. And among the different prosthetics component, we have a coefficient friction of 0.04 to represent the smooth surface of the insert and the femur component. We then have to decide which are the region of interest for our let's say, models. And since we want to analyze how the bone reacts to a change of constraint, we divided it in medial and lateral to also allow to analyze the results in terms of homogeneity, symmetricity, and so on. Same was done also for the insert. In fact, for each insert, we divided in 3 parts, and we checked for medial, central, and lateral section. For all of these regions of interest, we consider the von Mises stress, the average von Mises stress. And for the insert, we also check the contact areas and relative contact pressures. Now we have basically all the ingredients of the model. We have to decide what task we want to address. So as I said, we want to check something that the patient undergo daily. So first task that we checked, it's a static task during the landing phase of the gait. So when the heel of the patient is touching the ground during the gait cycle, because it's one of the moments when we have a really high force on the joint and we have a full extended knee. So as you can see, the configuration involves a 2,200 Newton load applied on the femur at 0 degrees of flexion. Then during the gait, we also have another phase in which we have high stress hysterics in the taking off phase. So also in this case, we considered a 2,200 Newton force applied this time with a specific angle and an angle of flexion of the joint. The third configuration that we then checked is for the standing up from a chair. So we start with the 90-degree flexion of the knee, and we applied a 1,000 Newton force. All these configuration relative forces are taken from previous literature studies. Now we have everything, so the last part to do before launching the simulation is to define the mesh, and what we did was to proceed with linear tetrahedral elements. The element size was chosen between 1 and 5 millimeter according to a convergence analysis that we performed, and the abacus was used as a solver. So we performed simulation and we got to the results. These are the results in terms of contact areas for the various model. In the table, you can see the different model of implant and the different configuration analyzed. And from the results, we can already see that the mobile bearing cruciate retaining ultra congruent is the one that presents the highest congruency, because its contact area it's up to 3 times higher than what we can find for the fixed bearing models. And again, even between general mobile bearing and general fixed bearing, we can see a great difference. So mobile bearing appear to be the one allowing the highest contact areas. If we then check the stress in the insert, we can see that the average von Mises instead is pretty constant among the different constraints of the implant. First thing, we can check that it's really low values because all of them are below 1.2 megapascal, but we can see that the concentration in the fixed bearing is once again more located in small areas, but overall the average are similar among models. Checking then on the bone, we can see that the distribution is kind of homogeneous among all the TKA models addressed, and it's mainly located in the cortical bone. Of course, we're gonna have different patterns according to the boundary condition we applied, but it's consistent, and we can see that the behavior is almost symmetrical. So the distribution between the lateral and the medial stresses are similar regardless of which is the implant and which is the boundary condition. If we then go and check the distal portion of the bone, what we can see is once again that the results are pretty constant among the different implants and the different boundary conditions, with the exception of a significant variation that can be found during configuration C, that is standing up from the chair, in which we can once again see a difference between the fixed bearing and the mobile bearing models, with the mobile bearing model showing a lower concentration of stress. So what we can deduct out of these results, we've seen that the contact area distribution is significantly different in case we are using a mobile bearing prosthesis over a fixed bearing one. But in all the cases that we analyzed, the values were still appreciable and satisfying. So even in case of fixed bearing, we have satisfying results, but the mobile bearing had higher contact areas. We have almost symmetrical medial and lateral distribution on the stress on the insert. This is not to underestimate as a result, and therefore it's significant that all the level of constraint were able to provide it. The stress distribution in the different region of the tibia were not remarkably different, with the only slight difference found between mobile bearing and fixed bearing in case of the standing up from the chair configuration. And overall, mobile bearing models presented the best performance in terms of kinetics for the highest congruency when compared to the other prostheses analyzed. So as a take-home message, we can see that changing the prosthetic level constraint did not induce remarkable variation in the tibial stress distribution, but instead it provided a change in the distribution of contact areas and the concentration of the stress for what concerns the prosthetic components interface. So when we are dealing with the insert and the femoral component. This information can therefore be useful for the surgeon when deciding which implant to go for with the patient according to the configuration and to the situation of bone and soft tissue that he finds in the patient. So I thank you for your time. If you have any question, feel free to contact me with the address reported, and I hope I didn't surpass my time limit.